when we were working in two-space, we were able to take a differentiable function in x and estimate it very well near some value x equals a with a linear approximation based on the tangent line. Well, the same idea holds true if we're working in three-space, but the linear approximation is now no longer a line. It's actually now a tangent plane. So suppose the following conditions exist. I'm going to say that S is a surface where z equals f of xy, and this function f has continuous first partial derivatives. The point x naught, y naught, z naught is a point on S. It's actually a point on the surface. And I'm going to call C1 and C2, I'm going to say that they are curves obtained intersecting that's kind of ugly. The vertical planes y equals y naught and x equals x naught with that surface S. So if I have all those conditions satisfied, the point P lies on both the curve C1 and C2. So now if I call T1 and T2 tangent lines, they're tangent to the curve 1 and curve 2 at the point P, then the tangent plane specifically to that surface S at P is defined as, that should be a D, defined as the plane that contains both T1 and T2, these two tangent lines. Now the tangent plane at P is a plane that most closely approximates the surface near that point P. Now recall that any plane passing through the point x naught, y naught, z naught will have the form a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, which we can write as, well, if I divide out the c and move the z over, I can say z minus z naught is equal to a over c times x minus x naught plus b over c times y minus y naught, which probably just simply end up writing as more compact. Just call this a over c the constant a, x minus x naught, and b over c the constant b times y minus y naught, which is, obviously the equation of a plane rewritten in this form. Now, suppose here for a moment, or consider the intersection of this plane with the point P that must occur at y equals y naught, and likewise at x equals x naught, but specifically when y is equal to y naught, then this component right here becomes 0. So that will give me z minus z naught equals a times x minus x naught. Now obviously this is for y equals y naught, like I said. Now, this is really nothing more than the equation of a line, where in this case, a is equal to the slope, and the slope here is actually going to be the partial derivative with respect to x. So what we really have here is z minus z naught equals the slope of the line, which is a partial with respect to x, times x minus x naught. Now, likewise, if I set x equal to x naught, then this component becomes 0, and I end up with z minus z naught equals b times y minus y naught. Again, this is the equation of a line with a slope equal to b. But this slope is going to be in the y direction, so that's really nothing more than saying z minus z naught equals the partial with respect to y times y minus y naught. With this idea, we can take it just a little bit further and say that the equation of the tangent line, the equation of the tangent plane at the specific point, I could write this as simply being z minus z naught is equal to the partial with respect to x at the point x naught y naught times x minus x naught plus the partial with respect to y at the point x naught y naught times y minus y naught, which all these x's and x naughts in there can get a little bit confusing. So I think it's probably easier just to write this similar to the way I did it up here. Simply saying the partial with respect to x times x minus x naught plus the partial with respect to y times y minus y naught. Now if we compare this approximation to the result of a linear approximation of a curve in 2 space, well, that's simply y minus y naught equals f prime at x naught times x minus x naught. See, this has the exact same form as what we're working on up here. Only difference is clearly our derivative will be a partial derivative, and we're working in 3 space, so we're working with x, y, and z, not just y. Now, I can equate this idea of this plane with the idea of the equation of a plane based on a point on the plane and the vector that's normal to the plane. So I can make a jump from here quickly and easily, to the idea of using vectors. Because what I have, I'm going to rewrite this, z minus z naught equals the partial of x times x minus x naught plus the partial of y times y minus y naught. Well, that implies that the partial with respect to x times x minus x naught plus the partial with respect to y times y minus y naught minus z minus z naught is equal to 0. Well, from that, I can look at this and say, well, gosh, I now know immediately that a vector that is normal, this normal vector is going to be fx, fy, -1. So the equation of my plane, I can write this as simply the partial with respect to x is vector, partial with respect to y, -1, dot, just like I always would, x minus x naught, whoops, thinking ahead of myself here a little bit, x minus x naught, y minus y naught, z minus z naught equals 0. So the solution to this will give me the equation of the plane, which obviously brings me right back to here, which is where I got all this from to begin with.